Welcome to another episode of Chemistry from Jay's House. So I'm going to assume that you understand how acids and bases work. I'm going to assume that you know that if it can donate a proton or a positively charged hydrogen ion to water and convert water into hydronium, then it gets the fun name acid. And if it can steal a positively charged hydrogen ion or a proton from water and convert it into hydroxide, then it gets the fun name base. So I'm going to assume that the mechanics of being an acid or a base, that you already understand how they work, and now we're going to get into the math behind it. I know what you guys are thinking. Math! Finally! My favorite thing in the world! By the way, that's sarcasm. So, I did not collect homework, I didn't go over homework, but I know what you guys are thinking. Jay sure talks a lot, but what's the point? That's right, let's go to the right, write the date. This, I believe, is slated for the 28th. Again, if that date's wrong, put the actual right date. Skip a line, go all the way left, right, the point. How does the pH, and note, P is lowercase, H is uppercase, and we'll talk about why that is, of acids and bases relate to 7. And that is the number 7. Whoosh. Does anybody know? Just kidding. I couldn't call on you even if I wanted to. Okay, a couple quick things. First thing is, when we write pH, it is lowercase p, it is capital H. That is correct. Kink. I will not accept things like capital P, lowercase h. Capital P, capital H. Or lowercase p, lowercase h. The only thing I will accept is lowercase p, capital H. Now the question is, why is that? That's a really good question. And the answer is because it stands for something. What pH stands for is the power of hydronium. The power of hydronium. And we remember that hydronium is H3O plus. So the reason that it is a lowercase p is because power is just the word. It's not a name or anything, so it's a lowercase p for the power. And the reason that it's a capital H is hydronium is an actual name. So P stands for power, H stands for hydronium, lowercase p, capital H, and nothing else. So the power of hydronium. And really what power means is not, in a He-Man sense of power. It is simply the concentration. How much hydronium is in there? So if we think back to drinking lemonade in the classroom, lots of lemonade, lots of concentration, and gave you a real powerful flavor in your mouth that you probably hated, unless you're Ben. Low concentration, not much lemonade, gave you not a very powerful flavor in your mouth. So it should be concentration of hydronium. This should be CH, but they went with power, which is kind of fun. Can't say I blame them. It's also French, by the way. Okay. So, here we are. How does it relate to 7? I notice 7's a very odd number. So, let's take some notes and let's figure out why it's 7 and not a nice number like 5 or 10, these numbers that we usually like in math. So, skip a couple lines so you can write the answer to the point, and then we have two notes. pH, lowercase p, capital H, a mathematical scale from 0 to 14. Of the concentration just barely snuck onto the screen of hydrogen ions. And then we need to take a note about the pH scale. Now this I'm not underlining because that's not a term. That's not a vocab term. It's just a thing you got to know. So that is something that runs from 0 to 14. And I wonder what's right in the middle. I wonder what is halfway between 0 and 4. Oh yeah, 7. And what that tells us is that 7 is neutral. If you have a pH of 7, you are neither acidic nor basic. And the nice thing about this is it's alphabetical. So everything from just before 7 all the way down to 0, they are all acids. So if you have a pH of 6.99, you're technically slightly acidic, though we'd probably just call you neutral because you're not really acidic enough to worry about. And if you're 7.01 out to 14, we would call you a base. So if you have a pH of 0 to just before 7, you're an acid. If you have a pH of just after 7 to 14, you're a base. And notice it's alphabetical. Acids are the low numbers, bases are the high numbers, 7 is neutral. So pause the video, write all this down, and then come back. Welcome back, because I'm sure everybody paused it. Okay. So, wait, didn't I say it was the power of hydronium? It was. It's weird that it says hydrogen ions. Well, that's because pH was originally found by taking an acid, originally, throwing it in, classic, a bunch of water, and then measuring how many of those waters changed into hydronium. So it was originally discovered as the power of hydronium. So then what we would do is we would test the water around the acid and we'd find out, hey, there's in this case, there were 7 water molecules, clearly too few to actually measure, but 7 water molecules, 2 of them changed, so 2/7 of the water changed to hydronium, so this is a little bit of an acid. If all 7 change, whoa, that would be a pH of 0. But 2/7, that's not a ton. So this is a relatively weak acid. And that's how pH was originally defined. But then scientists said, so wait a second, to measure the pH, I have to throw it in water? And people went, oh yeah, that doesn't sound super convenient, does it? No, I'd much rather find out straight from the acid. I'd love to be able to test the acid directly. So again, if we think of acid as having these acidic hydrogens, these single protons, these positively charged hydrogen ions, right? The question is, how easily does it shoot it off? Take that. And that's what the pH scale truly measures, is how easily does an acid rocket off its, what's this? Acidic hydrogen? Yes, it is. Or a positively charged hydrogen ion. It's also a single proton, right? Has 3 names. So what the pH is actually measuring is how easy does this come off? If it barely comes off, if it really requires a lot of energy, like the water almost has to tug on it to get it off, then you're not very acidic. If this thing is locked and loaded and ready to go and the slightest interaction has this thing firing off, then you're probably going to have a pH of 0. And we'll talk more about that in just a minute. But first, math. Okay, so let's draw a nice big scale. Let's have it kind of go across the entire board. And I'll draw it across the bottom. Okay, so 0's down here. 14's down here. 14's not even on screen. Come on, Bush League. 14, 0's just barely on screen, you can see that. Right in the middle will be our 7. Okay, so this is not a linear scale. pH is not one of these things where I would then be like, oh, if the concentration of hydrogen ions right here, if this is the highest amount, which would be 100%, or if we think of the power of hydronium, every single water gets changed, or every single acid rockets off, the slightest interaction, and every single acid, you throw this in, if every single acid shoots off, take that, rah! 100% of them interact, that'd be the highest scale, right? It's not a line like this. It's not a linear. So if you're halfway between these, you're not going to be halfway up. This is actually has to do with logarithms and exponents. So it's actually going to be this kind of a thing. So that's we're talking logarithms. That means if you go from, let's just mark this off. It's supposed to be a 6. The difference between 6 and 5, not huge. The difference between 1 and 0, enormous, right? So this is exponential, and base is the same way. Again, these are acids on this side. On this side, again, and we would think of this as also 100%, but this would be 100% of the bases eat protons. Give me that. Give me your proton. No, I don't want to. I say give it to me now. Okay. So if the base is super hungry and it eats all the protons, then it'd be considered the strongest base, which would have a pH of 14. And again, this is also exponential. Slightly poorly drawn. And these are bases. And again, let's do my absolute best to make this seem mildly accurate. Okay. Oh, you can't even see these numbers. Who invited this guy to be the teacher? I tell you. Right. Okay, so from 0 to 14, this is it. As you can tell, if you're looking at kind of 6 through 8, yeah, technically you're an acid at 6, but really? I mean, that means that most of the acids hold on to their proton, their acidic hydrogen, and don't shoot it off. Only a couple of them, the area kind of under this grub, just those little guys inside the triangle, go, take this, I'm out of here, woo! Except it's not an acid anymore. Yay, I got rid of it. But most of them are like, I've kind of grown attached to that acidic hydrogen. I'd rather keep it, just for a little bit, and we'll just see where it goes, right? So most acids would hold on, if it's a 6, most acids would hold on to that acidic hydrogen. And then you'll see that we don't get about halfway up until we're, way down by 1. So, slightly acidic, more acidic, but once you get down to kind of 0 and 1, now we really need to worry about ourselves and be very careful over here, Where over here, now you're talking more like lemon juice, right? Base is the same way. Once you get over 13 and 14, now you're talking very strong cleansers and soaps and stuff like that, lye, that you'd have to have the windows open when you use it, and bleach and oven cleaner, all that kind of stuff. We're kind of over in this area. Those really strong cleansers are at the 13, 14 area, and the strength goes up immensely as you get down to the bottom. So I strongly recommend pausing the video again and writing this down and doing your best to recreate this graph. It's super informative, so pause. Welcome back, because clearly you did that. There's no way you wouldn't do that. Oh wait, you're teenagers. Of course you didn't. Do something that's good for me? Nah, I'd rather get in Discord. Okay, so we haven't talked really math. I mean, sure, I wrote some numbers down at the bottom, but is that really math, a number line? The answer is no. But that's all the math I'm comfortable